Today, we're going to start playing the solving triangles game with solving right triangles. So remember that a right triangle will have a 90-degree angle and therefore will have a hypotenuse. Also, when we're dealing with a right triangle, that's going to bring the Pythagorean theorem into play. So we've got a lot of tools to play the game. Remember that our standard deployment of our standard naming convention for angles and their sides is side A will be opposite angle alpha and side B will be opposite angle beta. Since we're playing the right triangle game, we're definitely going to have a right angle, and C, because we like to use the Pythagorean theorem as a squared plus b squared equals c squared, that forces us to make C the hypotenuse, the side opposite the right angle. Here's the game of solving triangles. I give you 3 pieces of information about the triangle. You find the other 3. Always in the solving triangles game, I have to give you 3 pieces of information and then ask you to find the other 3 pieces of information. Sometimes it'll just be 1 of the 3, but that's the big picture of the game. Given 3, find 3. In the solving right triangles game, one of the 3 given pieces of information will be that there is a right angle. So in the solving right triangles game, one of the angles is 90 degrees. In the solving right triangles game, the right triangle part is one of the pieces of information. One angle is 90 degrees. So I have to give you the right angle, or that it's a right triangle. Then I give you 2 additional pieces of information, and then you can find the other 3 pieces of information. Given 3, find 3. The tools that we have available are that the sum of the angles in any triangle is 180 degrees. So in general, in our triangle, that means alpha plus beta plus 90 degrees, our right angle, is equal to 180 degrees. Since we're playing the solving right triangles game, and one of the angles has to be a right angle, we can simplify this to alpha plus beta is equal to 90 degrees. Or we could be fancy and say that alpha and beta are complementary. I'm never sure if complementary is a complementary or complementary with an E or an I. Because either way I write it, it always looks wrong. All right. Is it E? That's pretty good then. I was right the first time, but I looked at it, and it's one of those words that just always looks wrong. And I could never decide. Or I can never remember. That's maybe a worse sign than it actually is, than it actually seems. So one of the tools that we have pertains to the angles. The sum of the angles in any triangle is 180 degrees. Another of the tools that we have, since we're dealing with right triangles, is the Pythagorean theorem, a squared plus b squared equals c squared. The sum of the squares of the legs of a right triangle is equal to the square of a hypotenuse. So the first tool is exclusively angles. The second tool is exclusively sides. The third tool needs to bring those 2 things together. And that's going to be the trigonometric functions. Sine theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. Tangent theta is opposite over adjacent. What we need to be able to do is use the trig functions to solve for one of these sides, either use a trig function to solve for a side opposite, adjacent, or hypotenuse, or to be able to solve for an angle. So we got to be able to use the trig functions to solve for sides and solve for angles. Then we have to learn how to make our calculator tell us the information that we want to know. Got to make sure that we press the right buttons on the calculator in the right order, in the right mode, to make sure we get the information that we want. Then we got to learn some more technical details to make sure that we don't introduce rounding error so that our answers are precise and rounded properly so that we don't introduce rounding error. So the big goal that we need to do, we need to learn so we want to learn to use trig functions to find a side, opposite, adjacent, hypotenuse, and also find an angle. So we need to learn how to use trig functions to find a side and to find an angle. We also need to learn how to make our calculator tell us this information. In doing so, we're also going to need to learn how to round properly to avoid rounding error and report our answers correctly. We need to make sure, that we understand the difference between 2.4 and 2.40. First, we need to understand that there's a difference, and then we need to understand how we know which one to use. So let's get started. And we're going to start with an example. But I'm not going to fit it in this space. So pause for copying, and let's turn the page and look at an example. I like how this is going to be recorded, so pause for copying. You can actually just pause the video and write down what you want to write down. Let's suppose that we have a right triangle with in which beta is equal to 56 degrees and hypotenuse is 15 feet. Suppose we have a triangle in which angle beta is 56 degrees and the hypotenuse is 15 feet. So here are the three pieces of information you've been given. Angle beta is 56 degrees. The hypotenuse is 15 feet. The third piece of information is in the fact that I use the word hypotenuse. Since I've invoked a hypotenuse, that means we must be dealing with a right triangle. So one of the angles is 90 degrees. And there's our three pieces of information. So since we're talking about the hypotenuse, one of the angles must be 90 degrees. So let's draw a picture of what's going on here. I'm not going to draw the picture to scale. I'm just going to draw a triangle, a generic triangle. Excuse me, a generic right triangle. Where here, if I draw the right angle in this corner, and then the hypotenuse is 15 feet. This is a super generic problem. I don't know why I had to include units for the 15 feet, but I just wanted to make sure that we had the proper scope, but this is a big problem. Now, I need to assign the angle beta, and it can be wherever I want. So I'm going to say the given angle beta. I'm going to follow the convention that I used up here, and beta is going to be the lower angle. We could put beta at 56 degrees up here if we wanted, but I'm just going to say here beta is 56 degrees. I'm going to follow my standard naming convention so that the things that we're looking for are angle alpha, side B, and side A. The three pieces of information that we have are the right angle and the hypotenuse. Angle beta is 56 degrees. So that's our given three. The three that we're looking for are alpha, side A, and side B. Those are the three that we need to find. In this particular problem, we have two of the angles, a right angle and the 56-degree angle. When you're playing the solving triangles game, whenever you have two angles, just subtract to find the third. So in the solving triangles game, when you have two angles, subtract to find the third. That should be your first order of business. Whenever you have two angles, let's say as soon as you have two angles, subtract to find the third. That's the easiest of the calculations that we're going to make, so we'll do that. Subtract to find the third. It's not strictly necessary to do this, but it's the easiest one. You got to find three, go after the easiest one first. So I'm going to solve for alpha in this problem first. So alpha plus 56 is equal to 90. And so that means alpha is just 90 minus 56. And that's why I say subtract to find the third. So 90 minus 50 is 40. 40 minus 6 is 34, so 34 degrees. So you're already a third of the way done with the problem. Did I subtract that right? 56 and 34 is 80-10. So yeah. Arithmetic isn't my strong suit, so always watch out when I start doing arithmetic and I don't break out the calculator. Now, we need to make some kind of relationship between the sides and the angles. And we know that that means using our trig functions. Since we're going to be using our trig functions, we're going to need to decide what's opposites, what's adjacent, and what's hypotenuse. Now, hypotenuse is the 15. That's one of the sides that we're given. So if I look at this side B is opposite the 56-degree angle. So side B is opposite 56 degrees. B is opposite the 56-degree angle. I now have alpha is 34 degrees. So I could say that B is adjacent to 34 degrees. So now we have a big problem. We have to choose which one we want to use. So that's good news. We get to choose which one we're going to use. That's bad news. We have to choose which one we're going to use. And so now we're going to get stuck because like, oh, which one will be best? In general, use given information whenever you can. So I'm going to label B as being opposite the 56-degree angle. Side A is adjacent to 56. And A is opposite 34 degrees. So we have lots to choose from. I'm going to use 56. That was our originally given angle. So I'm going to say B is opposite the 56. B is opposite the 56. The other piece of information that I have is the hypotenuse. So let's find B. Let's make a note of that. So let's find B. So I'm going to observe that B is opposite the 56-degree angle. And I chose the 56 because that was the given one. The other piece of information that I have is the hypotenuse. The hypotenuse is 15. So what trig function uses opposite and hypotenuse? I've got opposite and hypotenuse.
Right.
So the trig function that we want to use with opposite, since we have opposite and hypotenuse, is sine. So I'll say sine. So I'll set up an equation. I'll say the sine of 56 is equal to opposite, which is B that we're looking for, divided by the hypotenuse, 15. So I'm going to say sine of 56 is opposite over hypotenuse. I love reading all the translations or transcriptions that Zoom is coming up with for hypotenuse. So now I've set up sine of 56 is equal to B over 15. I just need to solve for B. Since sine of 56 is b divided by 15, that means b is equal to 15 times the sine of 56. So I'll use this to say that b is equal to 15.0 times the sine of 56 degrees. And this is something that we can just punch into our calculating machine. One of the things that we're going to want to make sure of is that our calculator is in degree mode. So let's grab our calculator. Get rid of that stuff. Can't fit the whole thing. So the first thing we want to do is make sure that we're in degree mode. So we'll press the mode button and scroll down to where it says radian and degrees. So right now it will be in radian mode. So what you want to do is highlight the degree mode and hit enter. Oops, I didn't hit enter today. I want to highlight degree and hit enter. Now degree is highlighted. So if I move the cursor off of the degree, it's highlighted. So now I'll get out of the mode screen by pressing second and quit. And I'm just going to put in what I want the calculator to tell me. I want 15.0 times the sine of 56. I don't have to put degrees because I told the calculator that angles are going to be measured in degrees. Just close parentheses and hit enter. And we'll have 12.43556359. I'm going to round this. I forgot to tell you to round this. So I'm going to round it to the nearest 10th because I'm going to make it look like the 15.0. And I'm just going to say 12.4. This is a length. And since the 15 was in feet, the 12.4 will also be in feet. So now we're starting to fill out the information in the triangle. There's only one piece of missing information, and that's side A. So now let's find side A. Oops, let me scroll up. At this point, we have a choice to make. I have the hypotenuse and one of the legs. I can use the Pythagorean theorem to find the third leg. However, that 12.4 has been rounded. That makes it a little bit dangerous. We might introduce rounding error. So using the Pythagorean theorem might introduce rounding error. We can use the Pythagorean theorem with the 15.0 and the 12.4, but the 12.4 has been rounded, and that could introduce error if we're not careful. So let's try another strategy. Let's try to use the given information whenever we can. So I'm going to observe that A, the one that we're looking for, is adjacent to the 56-degree angle. And I also know that the other given piece of information besides the right angle is that the hypotenuse is 15.0. So now to find A, I'm going to look for a trig function that involves adjacent and hypotenuse. What trig function uses adjacent and hypotenuse? So what trig function should we use that has adjacent and hypotenuse? Checking our list up here. Cosine. Cosine involves adjacent and hypotenuse. So I'm going to set up a cosine. And I'm going to say that the cosine of 56 degrees is equal to adjacent, A, the side I'm looking for, divided by the hypotenuse, which is 15.0. I'm using only given information, and none of that has been rounded. And so I can solve the same way. If the cosine of 56 is A divided by 15, then A is 15 times the cosine. A is 15 times the cosine of 56. So I'll use my calculating machine and just do 15 times the cosine of 56. Calculator will still be in degree mode. And that'll give us an 8.387893552. That would be a ridiculous amount of information to write. So I'm just going to make it look like the other ones and say 8.4. And since it's still a length, it's still going to be measured in foots. So we've taken the 3 pieces of information that we were given, and we've solved for the other 3 pieces of information. We should do, there is a reality check that we can apply to solving triangles, in that the biggest sides will be opposite the biggest angles, and the smallest side will be opposite the smallest angle. And the middle side will be opposite the middle angle. This is known as the Brady Bunch rule. I'm just kidding, it's not known as the Brady Bunch rule. But notice that the biggest angle in a right triangle is going to be the right angle, and the hypotenuse of 15 is the biggest of the 3 sides we have. Then we have a 56-degree angle and a 34-degree angle. 56 is the middle angle, and it is opposite the middle side at 12.4. And the smallest angle, 34, is opposite the smallest side, 8.4. So at the very least, our calculations pass the reality check. Biggest angle opposite the biggest sides. We didn't get any negative sizes for angles. Everything at least seems to have worked. There are a few things that we need to talk about. I know that the problem has been solved and we should move on to another one, but there are more things that we need to say. Let's go back to this part. We can use the Pythagorean theorem with the 15.0 and the 12.4, but the 12.4 has been rounded. So let's say, what about that rounding error? There's no guarantee that we're going to introduce rounding error just because we use rounded information. It might be close enough for our purposes. So we did have the hypotenuse is 15. One of the sides, side B, is equal to 12.4, and that was rounded. But we have two sides and a right triangle, so we can use the Pythagorean theorem to find the third one. Let's see if it works out. Remember, we're looking for 8.4 for side A. So I'm going to take A squared plus 12.4 squared equals 15 squared. So A squared will be 15 squared minus 12.4 squared. And so A is just going to be the square root of 15 squared minus 12.4 squared. Notice that I didn't use my calculator on 15 squared or 12.4 squared. And I didn't subtract those numbers and then take the square root. This is because I have a calculator that will allow me to hit enter one time for this calculation. If you can hit enter one time, then you should hit enter one time for your calculations. I'm going to plug this whole thing in all at once. So I want the square root of a bunch of things. TI-84 opens up parentheses for us, and I want 15 squared minus 12.4 squared, and I get 8.44037879138. So rounding gives us 8.4. In this case, the rounding error did not show up. But look at the two values. The 8.387, that was not using any rounded information. But the 8.4403, we had rounded the 12.4. And those answers rounded to the nearest tenth the same way. But if for some reason I asked you to round these to the nearest hundredth using the 12.4, we're all of a sudden incorrect. Because 8.38 rounded the nearest hundredth is 8.39. 8.440 rounded the nearest hundredth is 8.44. The fact that we just had to round to the nearest tenth saved us from any rounding error. Now, we can avoid this rounding error by using more digits for the 12.4. So there's no rounding error in this case, but using more digits for 12.4 will reduce rounding error. So remember my target value is 8.38. Uh, 38789. This 8.4 was actually 8.44038. A little bit off target. The more digits that we use in the 12.4, the more on target we would be. In this case, it was close enough. But if I redo this calculation, instead of with just a 12.4 squared, I go with 12.44 squared. I round that to the nearest hundredth. Then I get 8.38131. So if I do 12.44, I'm closer to the target. If instead of 12.44, I use more digits from the 12.43556, I use 12.436. If I do the same calculation, but 12.436, then I'm even closer to the target. I get 8.38725. And similarly, if I use even more digits, it's about to go off the top of the screen. So 4356. I'm closer still at 8.38784. Now we're all the way down to the 4th decimal place. So more digits in the 12.4 gets us close to the actual target. Once again, in this particular problem, it didn't make a difference because I only asked for the nearest 10th, 8.4. That worked out right from the 12.4. But we need to recognize that more digits for the 12.4 will reduce the rounding error. The best practice would be to avoid having to use rounded information. Second best practice is to use your calculator's capability. So let's go back to when we first calculated that 12.4, when we did 15 times the sine of 56. We want to learn to use the answer key. Not the answer key, odd ones are in the back of the book or anything like that. I mean the key on your calculator that it says ANS. So on our calculator, the most recent thing that we did is 15 times the sine of 56. So we did 15.0 times the sine of 56. And that gave us 12.43556,359. Your calculator is actually keeping track of more digits than it's displaying. These are just the ones that it shows you. But there's more hidden off to the side. We don't need those. But the calculator keeps some extra ones to try to avoid some of this rounding error. So now the ANS key on our calculator, which we access above the subtraction key, it says ANS above that in blue. So if I press second and then the subtraction key, it brings up ANS. So now when we press ANS, it's a 12.43556,359 button on our calculator. So ANS. This is stored in your calculator. In ANS. Until you press enter and the display changes. But right now, we've got a 12.43556,359 button on our calculator. So instead of typing out that whole number, I'm just going to type as the next thing the square roots of 15.0 squared minus ANS squared, and then equals. There's actually not an equal sign or button on our calculator, so I'm going to hit enter. But here's what I'm going to type. I'll do the same calculation I had before with the Pythagorean theorem, and let's make the square roots 15.0 squared minus ANS squared, and then enter. And I get 8.38. This is what we got using cosine of 56 before. So this eliminates our rounding error as well. Use your calculator's capability to remember more digits so you don't have to type in so many digits. Also, don't write all these digits down. If I say round to the nearest 10th, then you only get to write one decimal place after to the right of the decimal point. So to the nearest 10th, this is going to be 8.4. If I ask for the nearest 100, that would be 8.39, and so on. The nearest 1,000. Will be 8 point, I have to write three things for the 1,000. 387. The next digit is an 8, which makes the 7 into an 8. So 387, 388. Whatever decimal place is called for, that's the last one that you have to write. So to recap, the best practice is to avoid using rounded information. Second best practice is to use the capabilities of your calculator to remember lots of digits, so you don't have to write down lots of digits, so you don't have to type in lots of digits. Sometimes we won't get to use purely rounded information, or sorry, unrounded information, just the given information. Sometimes we'll have to use rounded information, in which case we'll have to use our best practice, which is use more digits to avoid rounding. Any questions? How's everybody okay? That was a lot for one problem. It goes faster if you don't have someone trying to explain how the problem works. And it goes even faster if the person that's trying to explain the problem is not me. The reality check thing for the angles and the lengths is that the biggest side will be opposite the biggest angle. The smallest side will be opposite the smallest angle. And the middle side will be opposite the middle angle. In the problem that we have here, the biggest angle is 90 degrees, and so the biggest side should be 15. If we try to calculate B and got something bigger than 15, we know it's wrong, because 56 is smaller than 90. So side B has to be smaller than 15. Similarly, the smallest angle that we have is 34 degrees. So if side A is not the smallest side that we found, then something has gone wrong. So that's the quick reality check. It's not infallible. Sometimes you'll still be wrong when the biggest side is opposite the biggest angle, and so on. But at least if the biggest side is not the hypotenuse, you know it's wrong and you need to go fix it. So this is part one of solving right triangles. Let me do part two of solving right triangles. So I'm going to give you another right triangle, and we'll have some given information, but the set of given information is going to change things up a little bit. So let's suppose we have a triangle with a hypotenuse of 23.4. I don't want such a big problem as the last one, so I'm going to reduce the size centimeters. And one other side, let's just name it. Let's say side A is, now the hypotenuse has to be the biggest side, so I can't pick side A to be more than 23.4. I just need something smaller than 23.4. I will go with 17.9 because I need to come up with just something. And it should be measured using the same units. So I'm just going to make those 2 centimeters. Now, here's our 3 pieces of information. The hypotenuse is 23.4. Side A is 17.9. And one of the angles must be a right angle. So let's think about what we can use. Let's draw a picture using our standard naming convention. So I'm just going to draw a generic triangle. Here's our right angle. That means our hypotenuse is going to be 23.4. And one of the sides is 17.9. So if I say A is 17.9 down here, just following the same triangle that I used above, that means angle alpha is going to be opposite the 17.9. That means angle beta will be the other angle, and that means side B will be adjacent to the angle alpha. So we can solve for any one of these 3 things first. So that's great. We have a choice. But then again, that's terrible. Now we have to make a choice. So remember, our big principle is that we want to use as much given information in our calculation as possible. So we've got a 23.4 side and a 17.9 side. Both of those are represent given information. So we can use the Pythagorean theorem to find side B. We can start anywhere, but Pythagorean theorem is the first thing that we learn through all this. So let's use that first. So I'm going to use the Pythagorean theorem to find side B. So I'm going to say A squared plus B squared is C squared. So B is going to be the square root of 23.4 squared minus 17.9 squared. So B is equal to, and I'll just use my calculator for that part. The square root of 23.4 squared minus 17.9 squared. To the nearest tenth will be 15.1 centimeters. Third of the way done, just with the Pythagorean theorem. We didn't use any rounded information in this calculation, but the 15.1 is rounded information. So if I'm going to use that, I want to use my calculator and the answer key as much as possible. But let's try to avoid using that. I need to pick one of the sides, one of the angles to find. Let's find angle alpha. Now, I want to use as much given information as possible. Right now, B, which is adjacent to alpha, that's been rounded. So let's try using the 17.9, which is opposite alpha. So the 17.9 is opposite alpha. And 23.4 is our hypotenuse. So using given information, A is opposite alpha. So A is opposite alpha and C is the hypotenuse. And so that tells us we should use sine. Sine involves opposite and hypotenuse. So I'm going to say that the sine of alpha is equal to opposite 17.9 over hypotenuse, which is 23.4. And now we've come to the important skill that we need in this new version of the problem. Now we're using a trig function to find an angle. But the angle is inside the sine function, inside the trig function. So we need to use inverse trig functions to find an angle. We need inverse trig functions to find angles. So the sine of alpha is 17.9 over 23.4. So alpha, what we need to write, alpha is the sine inverse. To take sine inverse, you write sine, and you make a -1 like an exponent, even though it doesn't mean -1 as an exponent. And then we need parentheses, 17.9 divided by 23.4. The reason I wrote my fraction horizontal is that this is how I'm going to type things into my calculator. So to get the sine inverse function, we press the second button and then the sine key to get the what's printed in blue above it, sine inverse. So on our calculating machine, I'll press second and then sine to bring sine inverse. And then I'm going to do 17.9 divided by 23.4, and then close parentheses and hit enter. So it looks like alpha is 49.9 degrees. Now I've got side B I've got angle alpha, and I know it's a right triangle. And like I said in the first problem, as soon as you have two angles, subtract to find the third. So now, as soon as we have two angles, we subtract to find the third. So alpha plus, alpha is 49.9. 49.9, which is alpha plus beta, is equal to 90 degrees. So beta is 90 degrees minus 49.9 degrees. So I'll subtract 90 and I'll get 40.1 degrees. Any questions? Comments? Snide remarks? Notice that we could have used cosine, but that would involve for alpha, but that would have involved the 15.1 degree side. So I could have set this up by doing a cosine inverse of 15.1 divided by 23.4. The reason I didn't want to do this is that I know the 15.1 has been rounded. So if I can avoid using that, I will. And notice that our answer will be incorrect, because you would have said, if I said nearest 10th, you would have rounded that to 49.8, and I would say it's 49.9 to the nearest 10th. You have rounding error. And then you'll be all mad at me because I took off points just because your answer is wrong. But if I want your answer to accurate to the nearest 10th, then it needs to be accurate to the nearest 10th. Notice that if I use more digits in the 15.1, if I set up a cosine of inverse of 15.0714 and divide by 23.4, then that will give us the 49.9 that we're looking for. But we can avoid that entirely by just using the given information if we can. Any questions? Comments? Snide remarks? Here's how this game, what's going to happen when you play this game. I'm going to put a quiz on Canvas and I'm going to say find alpha. And I'm going to make the calculation using only the given information or without rounding it before I get there. And I'm going to say that the answer is 49.9. You're going to use the rounded answer, and you're going to come up with 49.8. And I'm going to mark it wrong. And then you're going to be mad at me. Took off points just because the answer is wrong. What a jerk. But all you have to do is go back, double check your calculations, make sure 50 is the right answer, and then just round it correctly. Or to what I think is correctly. There's an argument that could be made that there should be some kind of plus or minus in the answer. 49.8 and 49.9, I knew what I was supposed to do. Shouldn't that count for something? And my counter is, if you know what you were supposed to do, then your answer would have been correct in the first place. So the answer to use, whether it's 49.9, 49.8, or 50, depends on what I asked for as far as the rounding goes. So if I said round to the nearest degree, then you'd say 50 degrees. But if I said round to the nearest tenth of a degree, you'd round it to 49.9. So when it comes down to rounding error like that, what it kind of means is that I asked for a more precise answer than is really appropriate for the problem. But since I'm giving you an unlimited number of opportunities to land on my solutions, and I'm not going to be introducing rounding error on my end, at least y'all hope, I don't think it's unreasonable to ask for this level of precision. You can disagree with me, which means when y'all are teaching trigonometry, you can set up your rules with a plus or minus. But I see enough students that don't really know how to round answers that I want you to practice it. And that's kind of the reason that I do it. I want you to be able to round numbers properly. Once again, learning how to do trigonometry is part of this class. The other thing is I want to teach you math because math is being weaponized against you. And I want you to be able to defend yourself against math as a weapon. Any questions? It's not really about solving triangles. It's about learning how math works so it can't be used against you. From that point of view, I'm not so much your math professor as your defense against the dark arts teacher. I don't like to bring that up because that means I only have a lifespan of like one movie. So. Any questions? Comments? Snide remarks?
Brains melted.
That only seems like a lot to remember because it's a lot to remember. And you have to remember all of it in perfect detail. But don't worry about that. It just takes time. Spend time doing problems and it'll build up. It just takes time.
How much are those calculators and where can you get them?
This particular calculator I bought new many years ago. I think it was like $100 and something, and you can order them online. You can get refurbished ones. Yeah, in the 90s they cost $100. It's 2021, they still cost $100. It's just like Texas can't change how much it costs. They just decide. You can also get, it's a very good observation, you can also find them used. Sometimes make sure that there are good pictures of the used calculator. If you're going to get one on Craigslist or get one on eBay, make sure there are pictures that show that it's still in working order. If there are no pictures with the calculator turned on, I don't care how clean it looks, I would be suspicious. If you really want to be careful, someone selling a calculator should show you an empty battery compartment to show that there's not like it's not been eaten by corrosion. So there's that. Make sure if you get one of the ones with the backlit screen, make sure you specify that you're going to need the charging cord with it, although it's a pretty generic port. I don't know the name of this particular port, but that's the charging port if you get a rechargeable one. It's pretty common, but you might want to make sure that that's included. Is that a micro USB? It has a little USB symbol and it's small, so I'll trust you on that one. So you can get them used. Also, in the meantime, your calculator does have a scientific, has the sine, cosine, and tangent on it, but the way that you use them is a little bit different. If you're uncomfortable with that, we can set up an office hour and we can, I could just spend some time in class doing the calculations on an old style calculator with those buttons. In the meantime, if you're not sure how to figure that out, you can also just type these things into Google and hit equal, put an equal sign at the end of it, and it will run it like a calculator. So Google works as a scientific calculator as well.
Thank you.
Make sure it's in degree mode. All right. First sign off. That's going to do it for today. I will see you all on tomorrow, and thanks for playing. Stick around if you have other questions.